Today I'm going to be talking about something a little bit different and formatting and a little bit different than I have in some recent conversations. This is going to be more traditional office hours style or even lecture style, but I want it to be interactive as well. So I don't necessarily have a very long introductory monologue planned today because what I want to talk about broadly is the evolving conversation, both in public and in the climate science world, on climate sensitivity. I've gotten a lot of quizzical looks from folks recently when using that term, climate sensitivity, and to be fair, it's not very intuitive. What I'd like to be able to do today is explain briefly what it is, what the recent debate and conversation has been about, and what that tells us both about the world we're living in and also the state of climate communication, if you will. And I may be able to share some images on the screen to support that conversation. Additionally, today I was hoping to talk a little bit more about El Nino, but it looks like the November update of the multi-model ensemble suite isn't yet available as of today, so probably later this week we might talk about it more in the next session, but I will take some questions potentially at the end, and I'll probably have a blog post later this week that will discuss that a bit as well. So today, primarily, I'd like to have a conversation about climate sensitivity. So what is climate sensitivity is a good starting point for that conversation. And there are different definitions of it. You may have heard of transient climate sensitivity or equilibrium climate sensitivity or even something called Earth system sensitivity. They are different things, and when you're a scientist, it is important to distinguish between them. But for our purposes today, what I'm really talking about when we say climate sensitivity is the notion that the Earth has a particular amount of warming that it is subject to for a given accumulation of greenhouse gases in the atmosphere. So succinctly put, climate sensitivity is our best estimate of how much the Earth will warm for a given amount of greenhouse gas accumulation in the atmosphere. And the key point there, let me just make sure that since somebody was saying that the volume is low, that's an easy thing for me to quickly address. Well, it looks like it should be pretty, this is possibly why. Let's see here. Okay, so this should be clearer audio for folks. Sorry about that. Again, climate sensitivity is essentially our estimate of how much the Earth will warm for a given accumulation of greenhouse gases in the atmosphere. And of course, the main reason why the Earth is currently warming is, in fact, essentially the only reason within a reasonable degree of certainty that the Earth is warming, because all the other factors right now are so small by comparison, is the emission of greenhouse gases into the atmosphere. And so the challenge here is not only we don't know exactly how much we're going to emit moving forward, so there's uncertainty in essentially the amount that we're going to contribute to global warming through the continued combustion of fossil fuels and agricultural activities and other things like that, land use. We also don't know exactly, even if we did know the exact amount of greenhouse gases we were going to emit moving forward, the exact amount by which the Earth would warm as a direct response to that. And there's a lot of reasons why that's not an exactly known number. In fact, part of the reason is that the number itself, climate sensitivity, is a bit of a moving target. Paleoclimatologists, folks who study the climate from a deep Earth history perspective using indirect climate indicators like tree rings and river and ice core sediment records, or lake sediment records, because those are indirect proxies from the era before we had direct instrumental observation from thermometers or from rain gauges or things like that. First of all, those indirect proxies are useful, but they are indirect. They don't tell us exactly what was happening. And so even those proxies themselves are models, unlike when you have a thermometer today and you can look at it and say, well, that's, we're observing a particular temperature and subject to the measurement uncertainty, which is usually pretty small, we know what the actual temperatures are. That's not true for thousands of years ago or millions of years in the past. So we do have to rely on these indirect indicators, these paleoclimate proxies. But what they tell us is that at different points in Earth's history, the climate sensitivity has been different. So the same increment of greenhouse warming in the Earth's history has resulted in different amounts of actual planetary global warming depending on the initial conditions. So is the Earth already mostly ice covered, or is it mostly ice free? What is the configuration of the continents and the oceans? We're talking about millions of years ago, so those things do move around on long enough geologic timescales. We're talking about the axial tilt of the Earth. What's the Earth's obliquity? All of these things that don't change very much year to year or decade to decade, and therefore aren't meaningful factors in our current warming episode, but have been important in the deep past of the Earth. All of those different things can set the stage. In fact, even the Earth's temperature itself, what is the starting point when you have a bunch of extra greenhouse gases in the atmosphere? That itself can affect what the Earth's sensitivity to additional greenhouse gas accumulation is. If the Earth is starting off from a very cold state versus a very warm initial state, that can change. So not only is it a moving target and a dynamic one, so it inherently is going to have a range associated with it, we also can't measure that range with preciseness going back thousands or millions of years because we don't have direct records, but we have enough information from the paleoclimate record to start to get at least a distant handle on that. So this quantity, this climate sensitivity that we're talking about today, is itself something that probably changes over time. So it's not a fixed number to begin with. And then there are substantial uncertainties in how we calculate it, because we can essentially estimate it in two ways. We can estimate it going back into the Earth's deep history using paleoclimatology to estimate it from the record of what we think the Earth has done before. And we can also use models, numerical models, computational models like climate models, these huge systems of equations that are run on these supercomputers that approximate the laws of physics and chemistry and biogeochemistry in some cases, of the atmosphere, the oceans, and its coupled Earth system components. Those are the things we talk about all the time in a climate context. We can also use those sorts of tools to estimate the Earth's climate sensitivity. And oftentimes we need to calibrate one against the other. So if we want to think that the models we're using to simulate the Earth's climate today are believable, they generally, hopefully, will do a reasonably good job with these paleoclimate comparisons. So we validate them against the climate that we think occurred during different epochs. And of course, they're not perfect because no model is perfect. But these are often the best tools we have available to us because essentially we have the indirect proxy records from paleoclimate studies and we have numerical climate models. Fundamentally, those are the two big tools we have to understand climate sensitivity, to understand how much the Earth might warm for a given kick to the system, if you will. And this number has been, it doesn't tell us everything about climate change, right? It doesn't tell us about precipitation or regional climate extremes by any means. It's telling us mostly the global average temperature, which, as I've said before, is limited in how much it can tell us about what's actually going on in the world. But it is still a very useful heuristic. Even though it's indirect and a statistical construct, it tells us a lot about the overall macro state of the Earth at a particular point in time when it comes to climate. So it is an important number. And you can imagine if the range of climate sensitivity is very wide, then it means that there might be great uncertainty over how much the Earth would warm for a given amount of greenhouse gas accumulation in the atmosphere. And to a certain extent, that is actually the case even today, where there is a significantly wide range of estimates for how much the Earth might warm for a given level of greenhouse gas accumulation. In fact, we often express climate sensitivity as a function of a doubling of atmospheric CO2 for various reasons of physical and mathematical convenience. So if you doubled CO2, how much warming would you get is the simplest way of putting it. And so for a doubling of CO2, there have been estimates that have ranged anywhere essentially from, on the extremely low end, from about 1.5 degrees centigrade to, on the very high end, numbers that exceed 4 or even 5 degrees centigrade for a doubling of CO2. So that's actually quite a wide range. At the 1.5 Celsius or so on the extreme low end, and 5 plus degrees Celsius on the extreme upper end. So that's more than a factor of 2 in between them. And now part of that is because the sensitivity itself, as I mentioned, changes over time. It's not a fixed number. So it might be that there are some states of the Earth system where the sensitivity is much higher than in other states. That might be a function of temperature itself, or it might be a function of other things. In fact, we know that this is likely true to at least a certain degree, that this number does change over time, as I mentioned. So that explains some of the range, but it doesn't explain all of the range, and the rest of it comes from the fact that we simply don't have enough information to pinpoint it exactly. And the big question, of course, is, well, even if this number, this sensitivity, is different over time, what is it now? What is it going to be as we continue to warm this century? Because ultimately that's going to tell us whether we end up on the high end of projected potential warming on a particular emissions trajectory or on the lower end. This has been the subject of a lot of work in recent decades, and really for decades before that. So this has been a long-term challenge in climate science for really as long as climate science has been a discipline, and arguably even before climate science was its own discipline, because it brings together so many disparate threads from geology and chemistry and biogeochemistry and atmospheric science and physical oceanography and many other things as well, even thinking about the interaction between space and the sun and Earth as well. So the reason I'm bringing this up, why am I talking about all this right now? Well, there's been a bunch of recent news headlines about papers or preprints or blog posts by quite prominent climate scientists, including folks like James Hansen and Michael Mann, who are big names in the climate field and have been for a long time. James Hansen in particular has been in the field for decades and has produced a lot of influential work in the field. So these are pretty substantial names talking about the same thing, climate sensitivity, how much the Earth is likely to warm for a given amount of accumulation of greenhouse gases. And they're saying somewhat different things right now. And there's a few reasons I wanted to talk about this now. One is to emphasize that in science it's usually, in fact almost always, best not to focus on what any one person is saying, and that includes me, by the way. And I do try and frame our own work when we do publish studies and when I talk about them within broader context. As longtime listeners and readers are well aware, I definitely don't shy away from the caveats, but I think even more important than emphasizing the caveats is really placing any one study or claim or assertion into broader context. First of all, is there evidence for the claim? That's one key piece. But also, even if there is evidence, even if there's a new peer-reviewed study that's come out and supported these claims, as is the case presently with some of the work that James Hansen has put out along with some other folks, how does that fit into the broader field of understanding, the context of the full body of work to date? Because in science, generally speaking, individual studies usually don't overturn years or decades of work. Every once in a while it happens, and that's not to say that one study can't ultimately end up being true despite initial skepticism by others. In fact, there certainly is a long track record of that happening in science. But for every time that happens, there are hundreds or even thousands of one-off findings that don't generalize, that don't replicate. And so it is really important, I think, in general, to contextualize any new individual research finding, even if it's by a very well-respected research group or individual scientist, in the context of that broader literature. And so that's the context into which I kind of wanted to enter into this conversation today, because there has been a lot of discussion recently about how, for example, James Hansen's work that was published, I think it was this week or last, suggests a significantly higher climate sensitivity than had been the median estimate or the consensus estimate leading up to this point, on the order of 4.5 or more degrees centigrade. As that range I mentioned earlier, that's very much on the high end of the currently estimated range. But there have been other scientists who have pushed back and said, well, we're not so sure that this study really demonstrates what it claims to, and also, even if it does, there are a lot of other studies that have come out recently that point toward lower climate sensitivity, notably not on the low end of the spectrum. In fact, one of the disconcerting things that's happened in recent years is that as we continue to, as a field, assess the Earth's estimated climate sensitivity, we've chipped more off on the low end than we have on the high end, meaning essentially that the best case scenarios have largely been ruled out of very low climate sensitivity of like 1.5, even 2 degrees centigrade. Those appear to be pretty unlikely. Whereas we haven't found as much evidence to rule out very high climate sensitivity. So although this 4 to 5 degree estimate that just came out is certainly on the very high end of the plausible range, it's not necessarily outside of it. But I do think that's the correct way to be interpreting this most recent study, and often this is the correct way to, I think, interpret most new findings is in the context of what's come before. So the James Hansen estimate that was just published, for example, is at the very high end of the range of estimates that are currently viewed to be plausible as assessed by paleoclimate researchers, as assessed by the most recent IPCC report, AR6. So there's a few ways to think about this. One is that I don't think it's actually good news that we still can't rule out climate sensitivity as high as 4 or 5 degrees centigrade. That would be a big problem because it's significantly above the current median estimate used to project how much we're going to warm under different future climate scenarios. And the fact that that is unlikely but not actually outside of the range of possibility, at least, I think should give us pause, especially because we do now believe that many of the very low climate sensitivity estimates of recent decades probably are outside of the range of plausibility at this point. So although the median is much lower than 4.5 or 5 degrees centigrade, we still can't rule it out. And I do think it's important to think about what would happen if the real world ends up being closer to the upper envelope of our expectations. I think in any risk management context, I think that's a very important thing to do, in fact. But I still think that we need to be talking about it in the context, again, of it being a relative outlier, not a completely impossible, ridiculous, one that we should completely ignore, but to think about it not as overturning the pre-existing research, but adding to it and complementing to it and giving us yet more information about what the possible range of futures might look like. And to that end, I wanted to bring up, and I'm going to share my screen now. I haven't done that in a while, so hopefully it goes smoothly. But I wanted to share a few figures, and these should pop up momentarily. I'm going to try and keep my face in the screen. Let's see if this actually works. All right. That looks good. Just double checking that this is coming up the way it's supposed to. Good, good. All right, I see it. I'm just going to take a brief break while I set this up. You might see a commercial break or something in the meantime, but just bear with me. I'll take a sip of water and then we're going to dive into the imagery here. So just hold on 1 minute. All right, everybody, thanks for that. I don't know if you saw an ad or something in the meantime, but well, we'll figure that out later. Um, let me see what's pulled up on the screen here, and sorry for any technical difficulties. All right. So, and apologies if this is on the small side, but hopefully it's legible. I don't have any immediate way of resizing at the moment. What I wanted to first emphasize is there have been some related claims in these online debates recently that the Earth's temperature spike that we've seen this year, which has been extraordinary and record-breaking, there's no doubting that, and concerning, of course, represents some new mode of warming that we haven't seen before, and that is something that is greatly contrary to expectations. And what I want to emphasize is, although this year has been shocking in many ways, it isn't actually as unprecedented. Excuse me, let me rephrase that. As shocking as this year has been, it has not been, at least when you look at the long-term global average perspective, completely outside of the realm of predictions. In fact, it's actually remarkably, and the plots I'm going to show today are actually just quick reproductions from Michael Mann's blog post, which I'll add a link to in the recorded version of this conversation. What this plot shows on screen right now is the observed warming we've seen since about 1970 in terms of the global average temperature. And the black, so that's the red line, or the actual observed global average temperatures year on year. The black line is the ensemble average across the CMIP class models for the same equivalent years. So across all the models and all the members, what is the median or mean value for that particular year over time? And then the lighter shading, the gray on either side of this, of the red and black, just represents the range in model projections. In this case, it's a 95th% confidence interval. So just think about it how essentially 95% of the data points in any given year fall within the gray bound. So there's a fair amount of bouncing around within it. But when you take the ensemble mean, the observations have actually been really close to predictions over the past several decades, and that even includes this year. And I want to point out where 2023 falls on this. This is what Mike annotated the plot to illustrate. This green bar, you can kind of see the cursor on screen highlighting it. That's an estimate for where this year's annual temperature is going to end up. So the median is that we probably will see the warmest year on record in 2023. That's unfortunately no surprise given what we've seen this summer. But it isn't greatly out of sync with where climate models thought we were going to be this year. So as shocking as this year has been, and as dramatic as the global extremes in temperature and precipitation we've witnessed have actually been, we're not really outside of this central zone of predictions for what 2023 might have looked like on a global average basis. Now, in terms of individual extreme heat waves and individual extreme precipitation events, that may be quite a different story. But again, climate models are not necessarily the best tools for understanding those regional extremes, and so when the consequences for the regional climate impacts of that increase in global mean temperature are taken into account, you probably need to look elsewhere to understand here. But this is the first graphical item I wanted to illustrate today, just to point out the fact that there are, despite surprises this year in the biosphere when it comes to extremes, when it comes to this sort of heuristic quantity that I don't like in other contexts, but here is really useful to be talking about, predictions from decades ago were pretty good about where we were going to be. And even in this this forecast that was initialized all the way back in 2004 using the models that were available at the time, this year still falls pretty close to the median of where we thought we would be. Now, of course, none of that is particularly great news because that's a lot of warming, and the models are predicting a lot of warming. So the fact that we've seen a lot of warming is, again, it shouldn't be particularly reassuring, except to say that it doesn't look like the models are somehow missing some profound acceleration of the Earth's surface temperature. We would see it in this kind of plot, and we don't really see it here right now. But there is a caveat, and I want to get to that with the next image here. I'll scroll to the next one. Let's see. All right, so the other interesting piece of this conversation that's come up recently is the realization that the period during which global aerosol emissions, which are different from greenhouse gases, distinctly different, that was somewhat offsetting the warming that we otherwise would have experienced in recent decades, that the period of that offsetting was ending. And I know this plot is small, but it is somewhat deliberately so because I actually don't want people to focus much on the details. But the only thing I really want people to think about is what this plot is showing overall, which is, the title is The Time Evolution of Effective Radiative Forcing. What that really means is that it's a plot over time of different contributors that are going to change the Earth's total energy balance, potentially, and how that varies over time. So in this case, it's estimates going all the way back to about 1750, before the Industrial Revolution, before meaningful human-caused climate change, and extending all the way up to 2022, so the very recent past. And there's really only two things I want to point out here, well, maybe three things. One is that overall, although there have been individual years with big spikes from essentially natural events, in this case, a lot of them were volcanoes. You can see these as these big negative spikes on the plot going below zero in some of these years. Those aren't sustained for more than a year or two. They go away, and they essentially revert back to the baseline. But there's a couple of things that don't. And the main ones that don't are essentially the things that humans have done to the atmosphere. So in other words, if you notice, this black curve here is really what I want to primarily emphasize. And unfortunately, it looks like I'm having some connection issues. Haven't seen that in a while. I'm going to pause for a moment until that comes back. All right. Well, perhaps that's just on my end. But if for some reason apologies here, having a bit of a connection trouble. If for some reason it's just on my end, can folks let me know via the chat if you're having problems too? If it's just me, then great. If it's all of us, then I'll have to figure something else out. But anyway, I'm going to hopefully optimistically proceed as assuming it's just me and that no one else is actually experiencing any problems currently. Okay, well, maybe that is what it is in this case, which is better than the alternative. All right, so going back to this, the reason I want to bring up what is arguably, okay, I'm seeing that it's quite stable on people's end. Good, it's just me for once, that's nice. The reason why I wanted to bring this up is not to focus on the details, but it's to point out two things, primarily. One is that the net overall human contribution is positive. That's this black curve with the gray shading as sort of the uncertainty bounds on that. So after about 1950 is when you see this black curve really taking off. That's the net effect of the emission of greenhouse gases and other greenhouse gas, carbon dioxide and other greenhouse gases like methane, nitrous oxide, other things. This black curve, which from around 1950 accelerated as we headed into the 1970s, 80s, and 90s, and now has been more or less pretty linear at a pretty strong rate of increase since about the 1990s or so. This is essentially why we're having global warming. So this whole black area over here on the right side of the graph after 1950 is when the magnitude of the human contribution to net radiative forcing, meaning to the positive energy imbalance in the Earth's atmosphere, really took off. The other curve I wanted to emphasize was this lighter gray line. And you see that I'm highlighting it again with the cursor here. Hopefully you can see that. But this is the line that's below zero. What is that? That has to do with aerosols. And what are aerosols? Well, essentially it's soot. And it is essentially the kinds of particles that in the atmosphere tend to block sunlight, and so actually exert a net cooling effect on the Earth. So greenhouse gases, of course, mainly what's going on with this black curve suggesting a positive increase over time, that's global warming. This thin gray line down here at the bottom, aerosols, which increased from essentially the Industrial Revolution around 1850 all the way down to around the year 2000 when they leveled off for a few decades. But then they started decreasing. So still a negative number, but since 2000, global aerosols have been exerting less of an influence than they did at their peak a couple of decades ago. Now here's the problem. If you notice, between about 1900 and the year 2000, where the human greenhouse gas influence, this total anthropogenic warming, the big black line with the gray shading was increasing, this thin gray line, the aerosol effect, was decreasing. Well, I should say that the magnitude was actually increasing, but it was becoming an increasingly negative value. In other words, they were partially canceling each other out. So for a while there, we were essentially having the global warming that was occurring due to greenhouse gases at least partially offset by cooling from aerosols. That was as bad as aerosols are from an air pollution perspective, and they really are terrible. They kill millions of people per year due to air quality effects on human health. So there's been a very powerful motivation for regions to reduce and bring to as low to zero as possible aerosol emissions. The one downside, something that I believe it was James Hansen called the Faustian bargain, is that therein lies the rub. The trade-off is that even though we're improving air quality and preventing premature deaths from air pollution, we're now unmasking some of the warming that was hidden by these sun-blocking aerosols for the last several decades, and we're only just beginning this process. Because as the Earth, as humans, as societies clean up their industrial facilities and their power generation facilities, this aerosol effect is going to continue to revert closer to zero. So it's going to offset less and less of the warming that otherwise would have occurred. So of course, it's good news because we're not having as much air pollution, but it's bad news because it's going to allow for potentially a more rapid rate of warming moving forward. Now again, climate models know this. So this projected decrease in the aerosol concentration of the atmosphere is not some exogenous, unmodeled, unanticipated factor. This has been this effect has been long anticipated that it would eventually occur, and now we're starting to see it happen. That means that in predictions for the Earth's climate future, this is to at least a certain extent taken into account. So this is not something that is necessarily adding to existing predictions for how much warming there'll be in the future. It's already included. Now, whether it's included adequately or perfectly, that's a more important scientific question. So it is possible that the aerosol effect has been underestimated in some cases, but it certainly is present in predictions of how much we're going to see warming in the future. So this is not some completely new, unexpected thing. To illustrate that, there's one other figure I wanted to show. And again, I'm still new to doing any of these screen sharing things. These will get better over time. I apologize if it's difficult to see. Doing my best. The technical setup still leaves a whole lot to be desired, unfortunately. But at least it's holding together today. You know what? This one is sufficiently small and difficult to read. I'm actually not going to emphasize it in this conversation. So I'm going to stop sharing my screen for now to avoid people, to avert the eye strain. So I think just even with those two pieces of visual information, to the extent you're able to see, one is that we're not necessarily warming any faster on average than predictions for how much we should have warmed by this point. However, there is some uncertainty in why the Earth's energy imbalance might in fact be accelerating at least a little bit, whereas the surface temperatures on Earth don't appear to have accelerated greatly. There's some limited evidence in certain portions of the deeper ocean that there could be some acceleration in the rate of accumulation of ocean heat content, which is perhaps where some of that extra energy is going. It's not a great deal, though, either way, of acceleration. And so the good news and the bad news is there isn't strong evidence of accelerating warming or an accelerating energy imbalance. The energy imbalance may be increasing, and even a steady energy imbalance would be bad news, because that's all you need to get global warming is you just need a positive number in that energy imbalance and you'll get net warming. So if that number is increasing over time, it means that the cumulative energy in the Earth system might also be increasing at a greater rate. But so far we don't see really strong evidence of acceleration of surface warming. We don't see really strong evidence of acceleration of ocean warming. Now, I will say that doesn't mean that evidence won't emerge shortly. In fact, there's some evidence from climate models suggesting that there should be a little bit of acceleration of warming over the next decade or so, partly because of this aerosol unmasking effect, the Faustian bargain coming undone, as James Hansen has put it, where the suppression of the warming that we otherwise would have seen by aerosols is going to continue to decrease as air pollution from any number of places on Earth continues to decline. So in the U.S. and Europe, that happened a couple decades ago. In China, this is currently unfolding, where aerosol emissions are dramatically on the decline after having radically increased in the 80s and 90s. India is a major global population center where there has been less progress with aerosol emission reductions, but eventually India too is very likely to start reversing its aerosol emissions as well. So as all of this happens, the rate of warming might increase. If the rate of greenhouse gas accumulation remains relatively constant, but we remove some of this aerosol masking effect, then yeah, it may start to warm somewhat faster. But again, this is something that has long been predicted by climate models. This is something that is included to a large degree in predictions of what the future is likely to look like. But it's not good news, because it does mean that in fact there may be a period of faster warming coming up shortly. One piece of this that has gotten a lot of attention, probably an outsized amount of attention relative to its global impact, is the effect of recent decreases in global ship aerosol emissions. So some folks have posited that this is a primary cause for why this particular year, 2023, has been so exceptionally warm, or this cluster of recent years. The best estimates currently are that the effect of this short-term and the relatively quick decrease in ship-based aerosol emissions is on the order of 0.05 degrees centigrade. Keep in mind that this summer, our recent months have been as much as 1.5 degrees centigrade above the pre-industrial baseline. The ship aerosol emissions contribution to that is probably on the order of hundredths of a degree centigrade in an era where we're living with about 1.3, 1.4, 1.5 degrees centigrade temperatures above the baseline. So it's not a totally negligible effect, but it is, in relative terms, quite small relative to the other things that are going on. The number one thing being the accumulation of greenhouse gases in the atmosphere, global warming, human-caused global warming by far. And the number two thing, in all likelihood, being the strong El Nino event, which tends to result in temporary global warming of anywhere from about 0.1 to 0.3 degrees centigrade. So several times larger, at least, than the effect of global ship emission decreases in recent years, at least as far as we understand them now. But even that, still, El Nino pales in comparison to the influence of regular old global warming to date. So I don't think any of these are totally negligible, but some of them are clearly dominating. Greenhouse gases, number one, El Nino, number two. And then there's a few things that sort of fall into beyond the second place category. One thing that's also important to remember is that the contribution to aerosol decreases from the recent ship regulations is actually a pretty small piece of the total aerosol decreases. So I do think, and there is evidence, that the total contribution from overall global aerosol decreases, including from factory smokestacks and vehicle tailpipes, is larger than that 0.05 degrees centigrade that I mentioned earlier. That's just the contribution from the ship aerosols. So the total aerosol contribution of that unmasking effect is probably starting to become important and detectable. So, and it's going to get larger, importantly, as that aerosol burden continues to decrease and we unmask more and more of that latent warming. But it is still secondary or even tertiary to the primary cause of the warming, which is the greenhouse gas accumulation in the first place. And it's not to negate any of these factors, and it's not to say that we know with 100% certainty. There's still perhaps a slight chance that we're underestimating the relative influence of something like, the Hunga Tonga volcanic eruption or ship aerosol reductions beyond what I just mentioned. Or perhaps that the overall aerosol effect is stronger or weaker than we thought it was. Further complicating things is the recent realization across a wide sector of paleoclimate, contemporary climate, and ocean science sectors is that the spatial pattern of global warming matters a lot. In fact, it may be linked to bring it back full circle to what we were talking about earlier, to the climate sensitivity. So imagine you warm the whole world by 1 degree centigrade uniformly, where every place on Earth warms by exactly 1 degree, and no place warms more or less than that amount. Well, that actually might result in a very different level of climate sensitivity than if that 1 degree is asymmetrically distributed, as it actually is in the real world. But so the pattern, this is essentially called the pattern effect. And it may affect both our understanding of climate sensitivity, which makes it important in its own right, but also things like how reliable future predictions of the rate of warming are going to be, whether or not we are going to experience an acceleration in the rate of warming or not. And I don't think there's really clear evidence at this point. Again, just to reemphasize, I do not believe that there's strong evidence that the rate of warming itself has accelerated. That evidence could emerge because there are some plausible reasons why that might happen. As others have pointed out, that's still a very different thing than saying exponential growth. Fortunately, there is no foreseeable future where the Earth's temperature rises exponentially. There are some foreseeable things that could happen to make the Earth's temperature rise at an increasing rate, at least for a period of time before our global carbon emissions decrease. But that is very different than saying that we can clearly detect it today. And it's also very different than saying that, oh, things could go exponential. Because that's a very specific quantitative mathematical term that doesn't always mean, I think, what folks intend it to mean in a colloquial setting. But I will then, on the other hand, emphasize something else, is that even if the rate of warming continues at its current pace, that's actually very bad news, because of what it suggests about our relative inability to bend that carbon curve and to slow the rate of warming and eventually halt it, which is what we need to do. It also understates the degree to which we'll continue to see increasing climate extremes. Part of that is because there are processes in the atmosphere that are actually exponential. So the warming we're experiencing is not exponential. It's probably closer to linear than anything else, with the caveats I previously mentioned, subject to those. But the hydrologic cycle, for example, does have an exponential relationship with temperature. So even assuming, as we currently roughly observe, approximately linear warming, this is essentially what I refer to when I'm talking about increasing climate whiplash. So the acceleration of the hydrologic cycle, the increasing capacity of that atmospheric sponge, if you will, that evocative analogy I like to use. Maybe I need to get these sponge props so I can use them on camera. That atmospheric sponge increases in size by about 7% per degree centigrade. That is the definition of exponential growth, because it's a 7% increase, so a nonlinear exponential rate for a linear warming. Now, it's a relatively small exponent, so it's more like compound interest in a bank. You don't become a millionaire overnight just by putting $100 in a savings account. But on the other hand, this is the whole wisdom behind retirement savings, is that compound growth over time can catch you by surprise, and you end up with a larger number than you would have expected at the beginning. Well, not so good news is that is also how the hydrologic cycle works. We do see exponential growth at a rate that's not that different from what you'd see in a checking account. 3 or 4% intensification of the hydrologic cycle per degree Fahrenheit of warming. And the challenge there is that with all of these complexities aside and all of these uncertainties about climate sensitivity, about the linearity of the warming trend, about this aerosol unmasking effect, the breakdown of this Faustian bargain, and all of these colloquial expressions about having to debts having become due. All of that aside, and it's not unimportant, but just to put it aside for a moment, even if the only thing that's happening is we're experiencing linear warming, that's still a huge problem, because we're already seeing the effects that we are today with a relatively linear amount of warming. The effects in the Earth's system from that linear warming are not necessarily linear. In fact, there's now abundant and growing evidence that the effects on the biosphere, the effects on the hydrosphere, the effects in the cryosphere are not linear. In fact, those may actually be, in some cases, truly exponential in the mathematical scheme of things. And so I think that's still where a lot of my concern remains. A lot of this other stuff is interesting science, and I think sometimes it gets a little bit conflated with paradigm shifting breakthroughs in the field when someone comes out with a study that suggests that a particular number is significantly higher or lower than the consensus amount. Some folks will say, in fact, I've gotten emails to this effect this week, oh, well, you said that the science was settled, so it sounds like there's still a lot open to debate. And of course, that's, I think, in most cases, a willful misreading of the situation and what that language has been intended to connote in the past. But specifically, just to be really clear, When climate scientists say that the science is settled, it's not my favorite term, but it is used, and there is a reason for it. They're saying that the basic connection between greenhouse gas accumulation in the atmosphere and planetary warming, that is settled. We understand that. We know what's going on. We know that it's happening right now. When we say that the Earth has warmed and that human activities have caused that warming, that is settled at this point. But within that, though, there is still a lot of things that are open to genuine scientific debate. Climate sensitivity, as I mentioned, is one of them. The effect of the extremes. How are extremes changing in a warming climate? That's something that is continuing to be a very active topic of research, and perhaps is something that we've underestimated. Something I definitely think that was underestimated historically is the effects on the biosphere and on human systems, even from a relatively steady rate of warming. Because that rate of warming is still far faster than our societies and our ecosystems can adapt to it. And so linear in that context is not good news at all, because the effects are anything but. All right, so I do want to take a look at the comments section here. One thing I wanted to go back and quickly take a look at if there's any very specific questions, and then I'll take a look for more general ones. I think given the time, we'll shift El Nino to the next conversation. I'll have more data and information to discuss then. Anyway, the very short version is it's still there, it's still strengthening, and it's still going to be a player this winter. So that's the one sentence version. But to go back to the comments about what I've been talking about today, let's see here. So I'm still here. I'm just reading comments since I don't have any particular filter on this, so I'm just going through linearly. Speaking of linear things. All right. So Josue comments, I'm still a little confused about how the hydrologic cycle has an exponential relationship with the rise in global temperature. So I've talked about this in previous conversations, but I'll rehash the analogy now because I think it's a good time to do so. The analogy I like to use is that in a warming world, the atmosphere increasingly behaves like a progressively larger sponge. In fact, in this case, it would be correct to say an exponentially larger sponge, even for a linear increase in temperature. So what do I actually mean by that? Well, technically speaking, this comes from an equation known as the Clausius-Clapeyron relationship, which is very directly an exponential function. And in its most simplified form, it is in fact an exponential function of temperature alone. So to understand the water vapor holding capacity of air, to a first order, all you need to know is the temperature. You don't actually need to know anything else. There are some approximations and simplifications there, but it turns out that that approximation works very well for practical purposes in the real world. And it turns out that that number is close to 7% per degree centigrade, or about 3 to 4% per degree Fahrenheit, that the atmosphere's ability to quote-unquote hold water vapor, that the saturation vapor pressure, the technical term, increases exponentially in a warming climate. That means two things. Much as if you had a progressively larger kitchen sponge, on the one hand, it means that, well, the larger sponge can, of course, if you wring it out over the kitchen sink, and it's saturated with water, it's going to produce more water. Imagine wringing out a gigantic sponge versus a tiny sponge. There's just a lot more water that can potentially come out of it because there's a lot more water storage space in the bigger sponge. But the opposite is also true. With a larger sponge, you also have the capacity to absorb more water. So if you spill a glass of water versus a big pitcher of water, a small sponge might be good enough for the glass, but you're going to need a comically oversized sponge to soak up the pitcher that you've spilled. So that means that not only on the wet side does the ceiling on how intense precipitation can become rise exponentially in a warming climate by about 7% per degree centigrade, plus or minus, but the intensity of evaporation, potential evaporation, also increases by about 7% per degree centigrade of warming. So both the thirstiness of the atmosphere and the propensity of the atmosphere to produce huge downpours increases by about 7% per degree centigrade, literally meaning that it is an exponential increase on both ends, both dry and wet side of the hydrologic spectrum. That is the fundamental mechanism of increasing hydroclimate whiplash. In fact, we're writing up a big review paper on this right now, and I keep surprising myself with how relatively elegant these curves look when you plot them out. It is really that simple. It explains about 80% of what's happening to the Earth's hydrologic cycle. So hopefully that helps a little bit. Maybe next time I'll have a sponge I can pull out and actually show it in person. All right, let's see what else we've got going here. The next question is on the topic of the hydrologic cycle. The U.S. drought monitor data shows that California is currently out of drought. What are some climate sensitivity risks that could prevent us from keeping this designation in the next year? All right, let's see. A lot to unpack here. Well, the first thing I would point out is that climate sensitivity is not really something that changes the Earth's climate very much from year to year. It's an emergent quantity of the climate over decades or centuries. And it doesn't really affect how much warmer this year will be than last year or next year versus this year. Unless somehow, I guess the transient climate sensitivity might be relevant if somehow we manage to double the Earth's greenhouse gas concentration overnight, literally. Short of some planetary catastrophe, that is not going to happen. It would be physically impossible. So fortunately, climate sensitivity is something we think about more on the multi-decadal kind of timescale in terms of what it means for what's coming down the pike years and decades from now. Doesn't tell us much about what might happen in 2024. But I do think, though, that there is a connection here. What does the Earth's overall mean temperature look like this year going into next year? And it's already at record levels. It's still, today, I've been talking about this repeatedly since earlier this year, at record levels. And the really, by all indications, with a very strong El Nino event looking to be in the cards through at least winter, it's likely going to remain at record levels, global average temperature, through the winter. By the way, California and much of the West is likely to see a much warmer than average winter this year. I'll get to that in the next conversation. Certainly unlike last year in that respect, although it could be wet, which would be more similar to last year. But what does this tell us generally? Well, right now, the Earth is hovering, at least temporarily, around 1.5 degrees centigrade above the pre-industrial era. It doesn't mean we're going to be there indefinitely. It doesn't mean we've hit the 1.5 degree threshold yet, as defined by the IPCC, because that actually had to be sustained over years. So we've only just briefly exceeded it for a couple of months right now. Still significant. And the reason why it is significant, I think, from a hydrologic impacts perspective, is the Earth's atmosphere does respond quickly to increases in temperature when it comes to evaporation and precipitation. So that is something that will affect us this year and next year. The fact that this year is the warmest year on record, that means that, of course, perhaps unsurprisingly, some regions will probably see their warmest temperatures on record, as they did last year, again next year in 2024. But it also means that some regions will probably see their most intense hydrologic events on record. There will be extreme precipitation and there will be extreme drought in different regions over the next year that will be amplified, even beyond what we've seen in the past decade or so, because temperatures right now are so warm. That has not really anything to do with the Earth's climate sensitivity per se, but it does have to do with how much warming we've seen recently, the temporary jump in warming we've seen this year, the ongoing strong El Nino event, and that increasing atmospheric sponge. That sponge does increase and decrease in size from year to year as global temperatures scale. And so strong El Nino years are often years where we see a lot of global precipitation extremes, both wet and dry, depending on where you are globally. And this year will be no exception because it's occurring now on top of a century of global warming. We also have that strong El Nino event, so this year, next 6 months or so, are going to be prime time for global precipitation extremes. Is California going to be on the list of places that gets hit this year? We'll see, and I'll talk more about that next time. But that's certainly not outside the realm of possibility. But again, subject to a lot of caveats that I don't think I have the vocal capacity to continue to talk about in this particular session. Stay tuned for the next one. And also, for the blog post on this topic. I know I need to update the Weather West blog. I should have one later this week, focused on some of the more short-term changes we're going to see over the next week or so. Looks like there could be a pretty active pattern coming up. And then also talking about the rest of the season and El Nino and what that evolving thoughts on what that might mean for California. There was one other thing I wanted to touch on before closing today, and for once I'm making a comment in the comments section. But the publisher of my extreme weather and climate calendar for 2024, there will also be a 2025 version. Stay tuned next year. They're running a bit of a minor sweepstakes at the moment. If you're interested in potentially receiving a free copy of the calendar, just go to the link that I just posted in the comments section sometime between now and Friday, and they'll enter you in that competition for the opportunity to win a copy of the calendar. And they may be running a couple more of these between now and the end of the year, so one way to get one for free. Who doesn't want that? All right, well, hopefully this was helpful. Apologies for any technical glitches. Still working on figuring out how to get the screen sharing a little bit better. It's tough when it's split screen. Maybe I'll just go to full screen when I do that in the future for better visibility. But thanks again for bearing with me. I see that there's still a lot of folks on, which is always great to see. This has been a pretty technical day, so I definitely appreciate the interest and the ongoing support. So check out that sweepstakes for the free calendar. I'll probably be having another YouTube live session. Slight chance I'll do one later this week again, so this might be a twofer this week. If not, maybe next Monday. And keep an eye out for a blog post later this week as well. All right, so thank you everybody again, and I'll talk to you next time.